Hey guys, in this particular lecture, we're gonna continue on our journey of solving for the steady state distribution of this particular equation. Right? So, just to recap, this is the kind of discretization we had, and the Jacobian would look something like this. Alright, so let us start coding, and because it's a one-dimensional problem, we don't need any DMDAs going around over here, but yeah, we will need a 1D grid, something like this, right? So let us make a new file. So first things first, hash include stdio, not stdio, petsc.h, int main, int argc, char star arg, return petsc finalize. Alright, so let us save this as rxn.dfn.c, just to signify it's a reaction diffusion system. Alright, so first things first, we need to define the various things we will need. So yeah, so we're gonna need a DMDA, but in this case it will be DM, and we'll call it DA, and we're gonna need a SNES. Apart from this, we're gonna need a appctx, which is to hold the value of row, n, all these things. So appctx will define it as user because the user is going to supply it. We're going to need two vectors, one is u and one is u exact, just to make a comparison. We are going to need anyway, so let's continue on this. Whenever we need a new variable, we'll sort of declare it, and we'll need a DMDA local info for performing the loops, and we'll call it info. So the data type DA is essentially DMDA create 1D. Okay, so one-dimensional regular array, and yeah, this is the distributed array object. Okay, so we're gonna use this DMDA create 1D, and it will help us in creating the one-dimensional grid. Alright, so let's proceed. So we will need petsc initialize. We have petsc. Sorry, this will have ampersand argc, ampersand argv, null, and the help text. Right, then we will go ahead and let us first declare what the user context will be. So we have to declare the struct. So type def struct so this will be double. So what all things do we need? So we're gonna need row, we're gonna need m. Yeah, so we're gonna need row and m. We also gonna need alpha and beta just to specify the boundary conditions in terms of m. Alright, so let's declare that, and yeah, that's pretty much it. So we will define it as appctx, so that's the data type, Alright, so let us declare the data type over here. So we have user.row is equal to, so what was row? Row in terms of, rather m was in terms of row, right? Yeah. So let us define row to be 12. That way m becomes 1. So we can do this to the 12.0. Alright, user.m will be the square of user.row upon 12.0 comma 2. Well, it's a square, so we don't need to do this here. Then we need to define the alpha, so user.alpha will be simply user.m user.beta will be simply 16 times 16.0 times user.m. So we have defined all the parameters there are. Alright, so these are what is required after initialization. So these are just the user defined values. Yeah, so once we have the user defined values, we will have DMDA creation. So DMDA create 1D. It will require the communicator PETSc com world, then DM underscore boundary underscore none. So let me just show you the things that we require: the communicator, the boundary type, the dimension of the array. So let us declare 9 grid points. It's fine. Then what do we have? Number of degrees of freedom, stencil width. So number of degrees of freedom is 1, stencil width is 1. Then number of nodes on each processor, we will declare it to be null, because the PETSc will do the load balancing in case we have multiple processors. And lastly, we must pass the DA, that is the distributed array over here. Okay, so the stencil is 1 because we are defining the H on our own. All right, so this is it. This is how the one-dimensional grid is created. Then we must do the other things. So dm set from options, we have to pass DA. Then dm setup DA, and then we have to set up the application context. So there's a function dm set application context. So we must sort of tell the distributed array that whatever the variable or rather the parameters are, it has to be distributed over the grid. I mean, it's not required for this problem, but there may be a problem where this would be required. So we must pass to the array the address of the user defined context variables. Okay, because if it is not done, it will not be able to see that struct that we have defined like this, right? Okay, so now that we have this, we will create a global vector. So let me show this. So this is the command which will create a global vector on the grid DA. So it's the same as declaring the sort of associativity of u on d. So dm create global vector dA and the address of u gets passed. Now we will duplicate this vector vec. So we could have simply done create vector, but that's okay. Duplicate u into u exact. All right, then what we need to do is fetch the rather before fetching, what we will do is, because we need to pass this into the array, so dm da get local info, we will get it into the variable info. All right, so this is just because we're gonna pass info to the arrays because we need to loop over the grid points, so we will eventually need this. Okay, so then what should we do? So our road plan should consist of create the exact solution, because we will have to compare it eventually. All right, then we must create the SNES object. So creating the SNES object will require creating the Jacobian as well, and it will require creating the function callback. Well, in this case, yeah, we will need all this. We will need to create the function callback, and we will need to create the Jacobian as well. All right, so let's first create the exact solution. So what do we need? So let's first allocate, let's first create the auxiliary vector. So to hold the nodal values, we will create the auxiliary function. So double star u and star au exact, and then over here we will do vec, or not vec, dm da vec get array from dau exact needs to be put into au exact. All right, apart from this, what do we need? Yeah, that's all that we need. In fact, we need to pass u so that we can create the initial condition. So we'll make a single function which will create the exact solution and the initial condition. We can do it in one go. So dmda vec get array from da get u and pass it to au. So now that we have the objects, or rather we have assigned u exact to au exact and u to au, we can pass them to get initial conditions or get initial and exact. And we will pass to it the address of the info, and we'll pass the auxiliary matrices, and we will pass the user context, because to construct the exact solution we'll also need the user context. So what we can do is pass the address of user. So we will keep this form and create this function. So get initial exact. We can copy this. Oops. We can copy this and we can create the function over here. So the output will be PETSc error code. So this is the function. So info, instead of this we will have dmda local info star info. We will have double star au and double star au exact and void, or in fact appctx star user, because we don't want to typecast it inside. We can use it directly. In case you put a void star, you need to typecast it to appctx. We have done this in the previous example. We don't need to typecast that. So inside this we will create int I and double h, that is the grid spacing, which will be 1.0 divided by the number of grid points minus 1, and the number of grid points is held inside the info. So info mx minus 1. So this is the number of grids minus 1. All right. We also need double x, yeah, for I going from info access I less than info access minus, no, so I access to info access plus info xm I plus plus. And so where do we get this from? And we have used this in one of the previous solver. Is basically this bit of code. Because we're passing the address of info, we can use this kind of a link, okay, to address the content of the structure. Okay, so now we are essentially looping over all the grid points. So this is just a loop over grid points. All right, so inside this loop, x, the value of x will be I times h. That's fine. And au I will be basically this thing. So it's just an initial guess. So we are getting the initial guess inside this u array. So look, what is going on? We have the au array which we have passed from main. All right, we have get vec array, we are getting it, we're passing it, we are getting the initial condition inside this, and then we'll put it back inside u. So finally we need to eventually put it back. So dmda set vec set array dau exact ampersand au exact, and we need to copy this. This will be u and this will be au. So we're fetching the initial conditions to this and then setting it back to the PETSc vectors. All right, so aui will be equal to, it's the guess, so user alpha times 1 minus x plus user beta times x. So what it is it's a linear interpolation between the endpoints. So these are the two endpoints, and I'm saying it's alpha times 1 minus x plus beta times x. So when x is 0, the value of the guess is equal to alpha. When the value is equal to 1, this becomes 0, so the value is beta. Okay, so it's like an initial, it's like a linear interpolation. So this is the initial guess. Alright, so that's the initial guess, no problem. Now we need to set the exact solution. AU exact I will be equal to user m times PETSc power real x plus 1.0, and that is raised to the power 4. And this is not x plus, what was the solution? Yeah, 1 plus x. Okay, so this is the solution that we have over here. Okay, so that's the exact solution. Finally, at the end of this, we must return 0, and that's all well and good. So this is the function which creates the initial condition that we have over here. Finally, we can move on to the creation of the SNES object. So it's the same protocol. SNES create PETSc world, comma the address of SNES, right? SNES set DM. So we have to tell that this particular SNES is linked to the distributed array. So SNES comma DA. Now we must set the function call. Alright, so we must set here the function callback and the Jacobian. Alright, so the function has to be done locally because we're doing it on a grid. Okay, so the way to do it is, okay, let me show you that function reference. SNES set local function. What is it? dmdsnes set local function local. Alright, so it's a residual evaluation over a DM. Okay, so because the function callback in this particular problem is in the form of a matrix which is assembled over the DMDA. Okay, so that is why we need to do the following. So we have dmdsnes set function local over DA, and we must do insert values. So that is the way it is, dm mode function and ctx. So dm mode, finally we need to define the function as well. So the function will be form funct and the user context. So now let us go ahead and define this function local. Okay, so let's see error code. What was the, so it's a pointer to the function. Okay, let's see if there is an error, we can always fix it. Okay, so PETSc error code form funct and dmda. So we will have the same type of inputs. So dmda local info star info. What else do we have? We have the array, so double star u, in this case it's au. Okay, so it's actually a local function evaluation and we have to pass the handle to that. Okay, so we'll rectify it later. So the function should take as an input um, the info, because we need to perform a loop, then tmds. Yeah, so we need to wait. Okay, so it will take the u array and the evaluation of the function. So it will be double star af and the application context star user. So what we need to do over here is to create the functions in the particular problem. So the functions will be, where is it? The functions will be these things. Okay, so and those will be stored in af rather. Okay, so int I const double, because we don't want to change h. This will be simply, oh, we can just make it double. We're not going to change it anyway. Info mx minus 1. All right, so we need double to store x and the reaction term, or we can just hold it in x. We can define it later on. We will then input these things, uh, these particular things. Okay, so double x, what we need to do for, so we need this same for loop to loop over all the nodes. That's it. Then we have if I is equal to 0, then af I is going to be ui minus alpha. Okay, user alpha. Else if I is equal to info mx minus 1, that is the right hand side grid, or the other right hand side node, then af I will be ui minus user beta. All right, else you simply have the interior points. So the interior points are easy. So what is the function? So because it's happening locally, that's why. So first we need to have x is equal to I times h, which we have already defined. And yeah, so af I, like the ith function, will be in terms of the u which is on the local grid. So minus of u I plus 1 plus 2.0 times ui minus u I minus 1 minus other plus user row times h square times the square root of ui. So PETSc sqrt real ui. Yeah, so that's the way we will declare the function. And once it is successful, we will simply return 0. Okay, so we have gone ahead and created these functions. So all these functions are valid for j equal to the inner nodes. So these are all the inner nodes, because the residues will be calculated for these function evaluations. Okay, so we have dm set local function, okay, set function local, and it requires what? Let us see, da, then the PETSc error code, no, not the PETSc error, the insert mode, then the function handle to, so it needs the function handle. So we need to give, instead of giving the name of the function, we need to give the function handle. So we will say that form funct is of the type dmdsness function. Okay, so this will make it pass the function handle. It should run without even declaring it like this, but anyway, let's see if it doesn't work, then we'll think about it. Now let me make the Jacobian callback. So dmda set snes set Jacobian local. Alright, so even this will contain da, then the function callback, if I remember correctly. So dmda set Jacobian local, dmdsness set Jacobian local. Yeah, it's the same kind of function handle. So dm, then the function handle, then the matrices. Okay, actually the function handle should contain the matrices and the application context. Okay, so this should contain the function handle. So form jack, and the type of the function is dmdsness function, not function, Jacobian. Okay, it has to be of this of that particular kind, because when you set Jacobian, the Jacobian function has to be of this particular kind. Okay, all right. Then okay, so apart from this, we need to pass the application context as well. So the address of user. Okay, so then we need to create the function, but before that, snes set from options snes. Okay, so now we need to create this form jack function. So the form is the same as the above. It needs, well, we'll create it from scratch. So it's essentially going to return again an integer to say whether everything has run properly or not. So PETSc error code form Jacobian, not form jack, dmda set, not dm, local info double star au mat j comma mat p comma app ctx star user. Okay, it's the same thing. instead of passing the vector, we are passing the auxiliary vector. That's it. That's the only difference. Okay. All right. So int I, and for the Jacobian, we're gonna have to insert three columns. So int col 3, and they will keep on shifting depending on I. We need a double H, which we can borrow from the previous code. All right, and we're gonna need something which will store three values, because we will insert the three values. Okay, so then we'll do the for loop for, so we're gonna borrow the for loop. All right, now if I is equal to 0, so what is the Jacobian? We've already discussed this, but when I is 0 and I is equal to n minus 1, the Jacobian, the diagonal element is simply going to be 1. Alright, so let us encode that. So if I is equal to 0, then what should we do? V0 is 1.0 and call 0. It doesn't matter, we can choose not to give call because it's going to be the same location as I. So we're going to insert it at I comma I. So we're gonna do mat set values into P, and we're gonna insert one row. The location of the row is I, and we're gonna insert one column, and the location of the column is also I. That is why we don't need to bother about row. And we're gonna insert V, because we're gonna insert only one value. V0 is sufficient, and we're gonna do it as insert values. Yeah. In fact, when I is 0, or when I is equal to the last row, I is equal to info.mx minus, not info.mx, info mx minus 1. So when this is true, then this needs to be done. Okay, so we have to set the Jacobian to 1. Now when it is not the case, else what should we do? Else we have to construct the 3 rows and do it. Okay, so call 0 is equal to I minus 1, call 1 is equal to I, alright, and call I plus 1 is going to be, not I plus 1, call 2 is going to be I plus 1. These are the columns where we want to insert the values, alright. Now V0 is going to be minus 1.0, V2 is also going to be minus 1.0, whereas V1 is going to be this thing, 2 plus whatever this is. So it's going to be 2 plus h square times user row divided by 2 times PETSc square root real of ui. Right, so yeah, this is the Jacobian. So we now need to insert these values, obviously. So we set Then we simply do mat set values into P. We're gonna insert one row. We're gonna pass the address of I. We're gonna insert three values. We're gonna pass the column address. We're gonna pass the values to be inserted address and insert values. That's it. So using this, we have created the matrix P, and we're gonna then have to assemble the matrix, so we can borrow the program from the previous. So in fact, we'll need this entire chunk, because either you assemble it, if j is not equal to p, then you assemble j whatever the user has provided. Okay, all right, so looks good. So this is the way you call the functions. There's a syntax for it, and after this we have made all this. We simply then solve snes solve snes null, put the solution in u, and let us destroy whatever we had before finalizing. So rec destroy u exact, then mat dm destroy ampersand of da, and snes destroy ampersand of snes. So let's see whether this compiles or not. So let's create a new target. So rxn tfn. All right, so I've saved this. Let's see whether it compiles. Okay, there's an error, form jack and all this. Okay, let's see what the issues are. So okay, so DM setup does not require the user context. We just need to set up the application context. So DM setup or DM set application context DM and the address of user. Okay, so let's see if that error goes away. Unexpected. So have we missed semicolon somewhere? Okay, there was a small mistake. This is not set array, this should be restore array. Let me make it. Ah, there's a small spelling mistake over here as well. There's a small mistake over here as well. There's a small mistake over here as well. Well, I've cleared some of the mistakes, and they basically stemmed from declaring the variable inside the, as a function call to the, declaring the variable going into the function as au, but rather I'm using u. Well, that was the error. So now I'll remove the error. So in the functions control, okay, form jack, we have not returned 0. And what does it say? X is set but not used inside form funct. Okay, so we do seem to get convergence, but now we should now check it with the analytical solution. So let's see how we can check it. So we, at the end of this function, we have the solution inside U. So what we must do is compare it with the exact solution. So the exact solution was built over here. So we will do the same thing. Vec x plus y u comma minus 1.0 comma u exact, and we will return the norm. So vec norm u comma norm infinity and put it inside some err variable, and the err variable has to be of kind double. Okay, so finally we can print out the error. So we can do PETSc printf. It has to be done over the com world, and we will print percentage %d, that is the number of grid points, and the error as percentage %g, and this will be info.mx and the error variable. Okay, so let's recompile. Okay, so the error appears to be 0.003. Let's do a grid refinement. So because we have declared the default to be 9, we can do a minus da refine 3. So when we refine, we get a much better norm. Let us do a larger refinement to see whether things are better. Okay, so as we refine, things become much better and we get convergence. So this is the solution. For some reason it says x is unused, but the fact of the matter is x is actually used. I don't know why. It's quite weird to see that error. It's not an error, it's a warning. But I don't like to see that warning. Oh, anyway, so yeah, the solution is returned, and well, can we draw the solution? Well, let's see whether we have the option to draw the solution. Let us run it with refinement 6, monitor solution, draw pause 10. We don't have x. Okay, let me start xming, and now we should be able to show the. Okay, so the solution goes from, it did go from 1 to 16. Okay, it goes from 1 to 16. Well, there you have it. Just like this, we can solve a complicated problem. It's updating the solution depending on the number of iterations, and it's gonna take a while. So for large number of refinements, we do get a solution which is will converge with respect to the exact solution. And in this particular lecture, we have seen how to create out of a PDE. In this case, it was not a PDE, but in this case, it was an ODE. From that ODE, we were able to create a sort of non-linear optimization problem, if you will. We were able to construct the Jacobian of the discrete algebraic equations. We were able to construct the functions of those equations, and all those were done on a distributed grid. So do this on your own, learn it by practice. You'll see that doing all this is not at all difficult. And with this and this particular lecture, I'll see you again next time. Bye.